Hey, Kazu. Yes,
Okay, so please take away.
thanks, Kazu, and thanks everyone for inviting me to talk at this workshop. I'm Corey Adams. I'm from Argonne National Lab. I'm presenting some work from the NEXT experiment, and some of the authors listed here have also been closely involved in this work. So the NEXT experiment stands for Neutrino Experiment with a Xenon TPC. We're doing Neutrinoless double beta decay with Xenon with a similar TPC as we just heard about. Though I'll talk about some differences on the next slide. Predominantly, this is a Spanish and US collaboration. Most of the institutions are in Spain. There's also some contribution from Portugal, Colombia, and Israel. And our leadership is from Spain and the US. So I'm going to talk about results from the NEXT White experiment. NEXT is a staged program, so we started with a small TPC, and we're building our next 100 kilogram scale TPC currently. I'll present data analysis from data we've taken with the NEXT White detector, though. This is running in Canfranc, which is under the Pyrenees in Spain. You can see it on the map there. It's the red dot. And on the bottom left picture here, you can actually see the pressure vessel for this TPC, surrounded by its lead castle in the top right picture. So how does the NEXT concept work? You can see the engineering design on the left here shows you the active volume and all of the surrounding material. In particular, if you look at the right version, there's the PMTs on the left and there's a silicon photomultiplier plane on the right. This whole volume is under an electric field, so as an interaction happens, the electrons drift to the right. And right as the interaction happens, there's a quick S1 scintillation, which we observe with our energy planes on our PMTs. This gives us our T0 for the event. And then we observe an S2 when the electrons drift over to the EL region. They create a bright flash. We detect that with both the energy plane and the tracking plane. The energy plane gives us a great resolution for the energy of the event. So we just sum up all of the light we observe from the event. And on the right side in the tracking plane, we're able to localize depositions of energy. So we have a simulation based on G4 where we can simulate all sorts of background interactions as well as signal interactions and our PMT and SIPM responses. And for both data and Monte Carlo, we do a reconstruction paths where we find the X, Y, and Z position of the hits based on the silicon photomultiplier position and the T0 from the S1. And we get the energy from the tracking plane. And we voxelize all of the hits such that the total energy in each voxel is the sum of all the energy of the voxels is the sum of the energy, the total energy from the PMTs. The events, when reconstructed, look like this on the left. This is a bit hard to pierce into the interior, but you can see there's some low energy voxels on the outside and higher energy voxels on the inside. And if you didn't have this voxelization effect, you would have events that kind of look like what they are on the right. This is projected down into just a 2D view, XY view. And we're really searching for neutrinoless double beta decay, which, as the name implies, is 2 beta decays. And our main background event is a single beta decay of the same energy. The classical analysis to search for these is looking for the Bragg peak of the electrons. So it looks for 2 blobs, one at each end of the track, for a signal event, and only 1 blob because there's only 1 particle in the background events. Most of our backgrounds come from 4 main sources. You can see them on the top right. And to really achieve a great neutrinoless double beta decay search, we need 2 requirements. We need good energy resolution, so we can narrow down our window of events, and we need excellent background ID within that window. So we need to be able to discriminate it with high power single and double blob events. We can test this with some of our calibration sources, notably this calibration chain on the left. We start with thorium, and it decays eventually into thallium, and we get this spectrum you see on the bottom right. There's a big, long, sort of exponential feature of single electron scatters, and right above 1500 keV, there's a double electron peak from the pair production threshold. So this is actually a great way to do a data-driven analysis of single signal versus background in this detector. The data here is well modeled by a Gaussian plus an exponential decay. So this peak that you see in this histogram in the middle is signal-like. It has 2 electrons. It's a pair production event. And the rest of it underneath, which is an exponential shape, is background-like. It's a single electron Compton scatter. So this is not our neutrinoless double beta decay energy. It's about 1 MeV lower, but it's the very similar topology. And we use it as our testing bed for a lot of our analysis techniques, since we haven't actually observed any neutrinoless double beta decay events yet. Okay, so I'm going to talk most of the time today about applying AI techniques in Next. So one of the goals is we want to use AI techniques to do this topological selection. And there's some serious challenges here in that how do you know that the AI is working on data? And how do you test on a signal that no one has ever observed? So we have a couple assumptions here, but the basic solution is to use this double escape peak on top of the single beta exponential background as our testing ground to develop all of our techniques so that when we do our physics search for neutrinoless double beta decay, we're ready to go with our analysis. Some of the assumptions are the extrapolation from slightly lower to higher energy. We're assuming it's going to be the same issues to go from simulation to data at about an MeV higher. And we also assume that our accuracy of single versus double beta tracks is going to extrapolate roughly equally to the same efficiency at higher energy. But the nice thing is, because we know the statistical shape of our double escape peak as a Gaussian plus exponential, we can do a data-driven measurement of efficiency. So here, let me just show our network design. It's a fairly simple network. We really haven't done an intense study to try to squeeze the most out of our training our network in accuracy, and I'll talk about why in a second. But we just have this simple residual architecture. Everything is in 3D, so we're using 3D convolutions, and our network is a sparse convolutional network. We normalize the event energy to 1 for every event that goes in, so the network doesn't have access to the total energy of the event. So even though we're training it over this slightly larger range than our peak of events, it gets them all kind of on an equal footing. Okay, so talking about this data-driven evaluation. On the left, you can see after we've trained a network, its performance on Monte Carlo with the validation set. And we know for each event going into these bins what its true label is, signal or background. And then we make this fit based on this histogram after we've applied cuts or before, as you go through these plots on the left. And we say, okay, take the data, fit a Gaussian plus an exponential to it. And then if you integrate the area under the peak as the Gaussian, that tells you how many signal events you have. And if you integrate the exponential, that tells you how many background events you have. So you take all of your events from the beginning, and then you apply some cut, say at 0.5 or 0.81, these are just illustrative. You do the same fit again, and you compare in your Gaussian integrals how many events are left compared to your previous Gaussian integral. And so the statistical method lets you evaluate your efficiency for signal and background without knowing an event-by-event label. On the right, you can see the comparison on Monte Carlo again of your true signal and background efficiencies from the event-by-event classification and the fitted values obtained as the network cut is varied. And for background, there's a slight bias towards a higher efficiency in the fitting than in the true values, but in signal, it actually fits very well. So this method isn't quite perfect, but in general, it's pretty robust and it gives you a good estimate of what your efficiency and backgrounds are on the whole sample without having to have the labels. Okay, so when we train the network, just as an example, if you take all of the input data, you throw your network at it and you train it, you immediately see it overtrains, and you get a huge bias and disagreement when you actually run it on data. So in the top right plot, this is our signal efficiency versus our background rejection. The red is the true MC values. The red squares with the error bars are what we get from this fit. And the blue points are what we get from the fit on data. So this is, I think, quite poor. You get very bad performance on data, even though we were expecting to get good performance based on the Monte Carlo. The reason for this is well known. We don't have perfect Monte Carlo. No one does. And we know there are some key differences in our Monte Carlo to our data in things like track length, track energy, as you can see on this bottom left plot. So one of our techniques to mitigate this was to apply on-the-fly augmentation to our training data. So we targeted some augmentation filters that specifically obscure from our network all of these differences in data in Monte Carlo. So we shift the events around in the detector, we flip them in XYZ, we give them slightly different charges on the silicon photomultipliers, we zoom in and out to give the same event but with a different track length. And with all of those, we see better performance on our data, but we had to ask the question, how do we know if it's going to work when we get to the Neutrinoless double beta decay search before we can actually look at the data? It's important to be able to quantify this without looking at your signal region of interest and know that your network is performing well before you actually open the box. One technique we developed was to use sidebands. So they're highlighted in this histogram in the top right. We take these darker regions of events and we look at the output of our network one layer back from the prediction. So after it's gone through all of the network sort of as a feature extractor, we get this feature vector before it's turned into a yes/no signal or background. And we compare the samples from those features between between simulation and data as we're training. And we use this energy distance metric, which can help us compare two sets of data and to tell how far apart they are or whether or not they come from the same underlying distribution. And in the energy distance metric, a lower score means the two distributions are much more closely related. So we take these sidebands, and as we train our network, with and without augmentation, we track this energy distance. You can see here the left and right sidebands. In blue is with no augmentation, and in orange is with augmentation. And this energy distance tracks at a much lower value, almost an order of magnitude lower in some cases, with the augmentation than without. And this is telling us that the features learned by the network are much more closely related between data and MC when you have augmentation than when you don't have it. So I just wanted to flash the plots from before so I can flip back and forth more easily. But when you have this augmentation enabled and you're tracking it with the energy distance to know it's working, you can actually really get significantly improved agreement in your output of your network between data and Monte Carlo. So you see in the top right in particular, it looks many times better than it did without augmentation. So the cost of this, unfortunately, is the overall performance of the network is somewhat reduced. Doing this augmentation is effectively a regularization technique. And so we've limited how much our network can fit to this exact domain in simulation, so it has to extrapolate to a different domain, albeit related in data. And so its overall performance is degraded. That said, the data import performance is dramatically improved, and that's what we care about. So this gives us a big boost on data at the cost of perhaps limiting our overall network. Ideally, some solutions would be to improve the Monte Carlo, and of course we're working on that. But this is a great technique to demonstrate that, yes, we can take our neural networks and understand how well they're going to do on our data before we actually open a box. So just to summarize, I think I'm staying in time, I hope. I believe we've shown in Next that it's possible to understand the performance of network data on data after training, even if you have imperfect Monte Carlo. So we've used here a couple of different pieces. We have data-driven metrics. So this Gaussian plus exponential fit allows us to measure our efficiency and background metrics without having labels on our data. We used appropriate regularization to obscure some of our domain differences between data and simulation, particularly these augmentation techniques. And we have appropriate tracking metrics. Here it was the energy distance on the sidebands to know that we're actually improving things as we're training without opening a box of, say, significant events. And on the right, we can see our figure of merit, which is very similar to the one we saw in the previous talk. Our data and Monte Carlo figure of merit is significantly improved that is from the one that would be without any regularization, and we're still beating the classical results, even though we've limited how much our network can learn. Thank you. I'm happy to take questions.
Thank you, Corey. Your timing is perfect. Thank you very much. And so let's take a look at the questions. And how do I do this? This time I will try to maybe share it. I'm sorry. Okay, maybe it works. Let's try this. Yes, I think so. Okay, so here you go. So there are 3 questions in the order with some upvote. Rather than maybe me reading, Corey, would you mind go over these questions and just try to give some answer?
Yeah, so the first question here is basically asking, could you get a higher energy peak to do further validation of the network's performance? That's a great question. And the answer, of course, is yes, we want more peaks that look like signal versus background where we can do a search. We focused in on this one because we had this data readily available and fairly well understood. And additionally, it had a classical analysis to compare against. I think in an ideal case, you would actually want to be training a network across energies. So you let it know how much energy the event has, but you give it fake simulation with 2 electrons versus 1 electron across a whole broad energy range. And then you can zero in on multiple double escape peaks in your data and actually do this data-driven validation across an energy range. And you would get a much better understanding of how you can extrapolate this to the signal energy region of interest for your neutrinoless double beta decay search. I hope that answers the question. I will ask this next one. What is the position resolution here? How well do these reconstructed tracks match the true trajectories? The answer there is quite well in terms of, is the true trajectory inside of the reconstructed trajectory? And unfortunately, as you saw from the images, I'm not still sharing, so I can't show you the images anymore. But the reconstruction in 3D gives you a rather broad image, and the actual track is very narrow. So we're looking at several orders of magnitude broader tracks in terms of just the minimum and maximum X and Y location. We have a very good understanding of this mechanism, and in fact, a parallel analysis led by some of the collaborators on this analysis is doing a deconvolution of this reconstruction to extract the true value. And we can feed that into our neural networks and actually get a much better performance boost. So I think the position resolution here is that I'm showing results with is well worse than the one we can ideally achieve. And so that analysis is also going in parallel.
Corey, sorry to interrupt you. Would you like to show your position resolution stuff? And then maybe you can also continue the next question, which is the data augmentation work, which you might also want to show some pictures.
I'll share again.
Yeah, so let me stop sharing and then so you can share.
Okay, here's the pictures of our data. So you see on the left, each of these square blocks in this 3D image on the left is 1 centimeter by 1 centimeter. And you can compare that to the resolution in the images on the right. So these tracks are widths of millimeter maybe that you see on the right. So the images we're feeding into the network here are much coarser than the ideal image. And ideally, these 2 paths of neural network reconstruction and image deconvolution will converge. And we have some preliminary results that show they look very nice with that. Okay, so let me talk about the data augmentation. So here is some of the filters we apply. So there's things like translation in XYZ, flipping in XYZ, zooming in XYZ. These are applied randomly on the fly. So we pull up a batch of data, and for each image in the batch, we basically have a binary switch, yes or no, for all of these augmentation techniques. And as we train, events will come in again, and they get a totally different selection of augmentation techniques with the same label. Our goal here was to build a set of augmentation techniques that's label preserving. So a single and a double beta event is still a single or a double beta event under all of these augmentation techniques. And by applying them on the fly randomly during training, we extend our domain of applicability of our network, essentially. Is there more to that question, Kazun?
This is just one more, which I don't think, I think I can just read it off. How did you arrive at the specific network architecture?
Yeah, so the specific network architecture was based mostly off ResNet. And there's not a great compelling story about how we arrived at it. I think we could take our network architecture and do some optimization techniques and really squeeze the most out of our network to get a better performance on Monte Carlo. And if we did that, we would find that it's meaningless because it doesn't work on our data. So we really focused in on understanding our data Monte Carlo performance of a network first. So the only feature that's particularly compelling about this network, maybe there's two features. One is that it's a 3D convolutional network, so we take the full 3D image instead of 2D projections. And second is that it's a sparse network. So all of our data is very sparse, sub 1% in terms of number of occupied pixels. And training with a sparse network gives a trained network in about an hour versus training with a dense network takes a bit over a day. So we can get a much faster return on our training with a sparse network. And the performance of sparse versus dense is comparable.
All right, thank you very much, Corey, for the nice talk and all the smooth answers.